All right, it's 10:45. Let's get started. As a McAllister alum, I am extremely excited to introduce you to Leslie Myint, who is the assistant professor at McAllister College, and she's going to talk to us about organizing knowledge from research literature using graph databases. Leslie, take it away.
Thanks, Kim, and I really appreciate the invitation to speak here. I think you, Diana, and Renee, this is just a really fun event. So my talk today is going to be about a lot of ideas, essentially, a lot of ideas that have been really nagging at me, really floating in my mind for a very long time. And in total, it's a lot about, honestly, it's a lot about reading, and it's a lot about gaining insight from human knowledge that's presented as text. So a good motivation, I thought, to this whole idea is this quote by Isaac Newton. If I've seen further than others, it's by standing upon the shoulders of giants. So it's this idea that, you know, we make progress, humanity, we make progress over the generations by accumulating all of this knowledge in our respective disciplines, sharing it with each other. And this is sort of the foundation that lifts us up. That's at least the idea. And I hadn't been to the Google Scholar homepage in a long time, but I thought it was funny as I was making this talk that literally the tagline at the bottom of Google Scholar is this quote by Isaac Newton, standing on the shoulders of giants. So all is well and good, but let's say that I wanted to start standing on the shoulders of giants. So what would I need to do? I need to read a lot. So, you know, I might search something in Google Scholar. Something of interest to me is, as a statistician, I'm very interested in causal inference. And within causal inference, this subfield of statistics, there's a sort of branch in ideology related to graphical models for making, for facilitating causal analyses. And if I just search this in Google Scholar, I would turn up about 147,000 results, which is extremely daunting, given that this is a subfield of statistics. If I wanted to become knowledgeable about graphical models and causal inference, I'd have to possibly learn about 147,000 different research articles. That's kind of scary. But, you know, it's likely that not all of those results are relevant. Even just in my paper pile account, which is my collection of research articles that I've sort of filtered down and identified as being relevant and particularly meaningful to me, I have over 1,000 papers. And it would be ambitious to say that I've read all of those thoroughly. I've read a lot of them, but, you know, even if I had read 1,000 papers fully, maintaining all of that knowledge and sort of augmenting my knowledge structures would be hard. That's just a lot of information. And so another quote to kind of motivate this sort of problem of so much reading is this quote from this book that I'm currently reading and really loving called Range by David Epstein. And it's a quote where David Epstein quotes someone else, actually. So Don Swanson is a peculiar personality. He got his PhD in physics. He spent some time in industry being a computer systems analyst, and then he went on to become the dean of the University of Chicago Graduate Library School. So like physicist to computer systems analyst to librarian. And he said this: the disparity between the total quantity of recorded knowledge and the limited human capacity to assimilate it is not only enormous now, but grows unremittingly. How can frontiers be pushed if one day it will take a lifetime just to reach them in each specialized domain? I really loved this quote. When you find a quote that resonates with you as deeply as this one did for me, you kind of cling on to it and sort of use that as a beacon or sort of like a North Star. And this quote just capitalizes so well on this idea that, you know, we are making progress. Like all of us, scientists across the globe, we're doing it. We're creating knowledge. But, you know, one day we're going to have to assimilate all of that knowledge and, keep it in our mental models, one day that will take a lifetime. And that's really scary to me, at least. So kind of putting this idea into my own words, how can we stand on the shoulders of giants if we don't even have the ladders to reach them? And sort of thinking about this, I was reminded of a really funny moment from the Mummy movie. So Evie is a librarian in that movie, and she really proudly announces after one point in the movie, after like a really cute drunken stupor, that she's really proud to be a librarian. And I, in this context, am sort of envious of librarians and the skills that they have to just be like, just have hands and arms in so many different fields of knowledge. I think that that type of thinking is extremely valuable. And it's a type of thinking that is just ever present in my mind as like in the ideas that I will talk to you about. So broadly, what am I trying to sell in this talk? I'm hoping to sell to you a mindset. I'm hoping that we can cultivate mindsets for a particular idea. I hope that we can move towards ways of interacting with knowledge to facilitate sustainable pattern finding. These vast swaths of knowledge in these different domains, really the meaning that comes out of it is finding patterns. And, if we can't really reasonably read everything, what can we do? So I hope to tell you a little bit more about that today. So in thinking about this, I actually spent a lot of time this summer sort of relearning how to read, in a sense. And what I mean by that is I spent a lot of time thinking about how to learn to read again effectively and sort of produce sort of digital artifacts from what I read. And let me show you what I mean by that. So I try to revise my note-taking system for when I read research articles. And this is just an example of a particular note that I took, a set of notes that I took on a research article about a causal inference method called principal stratification. And in particular, I tried to, at the end of my reading, to synthesize sort of what I thought were the key takeaway concepts into these really relatively small digestible forms. So for example, you see that I have these hashtags for these different ideas. I tried to synthesize the ideas that I thought were important in a way that I had sort of this uniform language for linking different ideas. So like I tried to use ISA as a particular linking. So like, is the idea on the right a synonym for is the idea on the left a synonym for the idea on the right? I tried to use useful when to indicate when the idea on the left is a particular instance for using the situations on the right. So I tried to come up with these sort of hashtag linking structures to kind of create as digestible nuggets of knowledge as I could. I'll tell you a little bit later about sort of the motivation behind me trying to come up with this sort of uniform verb structure. So I'll say more about that in a little bit. And kind of the idea about these digestible nuggets that I was trying to create as my summaries of research articles, I think is well motivated by this tweet thread by Daniela Witten. She posted this a little while back as part of the Women in Statistics Twitter handle. She had this really great tweet thread where she was like, let's play a game. Let's play a game called It's Just a Linear Model. And she goes on to describe various things. And the funny part of it was that she's super witty. I am not doing her justice in explaining her tweet thread, but she goes through a lot of different statistical models essentially and says, hey, by the way, it's just a linear model. So right here is the linear regression model formula. What about lasso and ridge regression if you're in the machine learning setting? Those are just linear models as well. It's just they're fit using penalized least squares instead of ordinary least squares. So at the time I was like, this is a classic, awesome Daniela Witten thread. But as I was thinking about this talk, I remembered it particularly for the reason of her phrasing. It's just a. And I think that this is a goal that we can try to achieve in terms of, well, for me, it was a goal that I was trying to achieve in sort of summarizing the insights I was gaining from research articles in a small, digestible way. It's just a, right? It's almost a goal to reach the level of understanding where you can say it's just a linear model. And so that kind of motivated my thought process as I was trying to summarize insights from knowledge. So this leads me to sort of a guiding question for the work that I'm trying to do in this area. What are the atoms, in a sense, of concepts in statistical fields? I'm reading the research literature to become a better statistician, to have these better insights about new subfields of statistics. How can I break that down such that, how can I break down those complex ideas into essentially the fundamental building blocks of those ideas? I'm really interested in that. And sort of more broadly speaking, you know, atoms are the fundamental building blocks, but they make up molecules. Molecules make up, you know, possibly cells if you're in a biological system. I'm interested overall in what the overall structure of statistical knowledge is. And sort of returning to the particular setup that I used in my note-taking, the particular sort of data structure that I had in mind when I was taking these notes is actually something called a graph database. And I want to say a little bit about what that is. So a graph database it is a database. It's a way of storing data, but it's an expressive and memory efficient way of storing particularly interconnected data. And I'll say a little bit more about this later, but one of the capital features of graph databases is that you can query them in ways that are very different from traditional sort of rectangular relational databases. And that ends up being very powerful. And I'm wondering if this will end up being a good way to represent information from text, essentially. But let me tell you a little bit more about graph databases. So graph databases can be represented pictorially, and I think that's another great feature of them. So for example, stepping away from the context of research knowledge in papers, you might have a system where you have users interacting with a product that you're making. So Alice is a user, and that is indicated by the user tag. Alice is a node, a person, a user in this graph. So is Bob. And they happen to be related to each other because they're friends. So there's this friend of arrow linking Alice and Bob. Oh, so I said this a little bit, but the circles are nodes, so entities of interest in your system. The user is the node type, and name has a colon after it because it's a property of the node. Friend of is a type of relationship. There can be other types of relationships between entities in your system, and relationships can also actually have properties in graph databases. So, you know, they might have started being friends in 2015, so there could be a since property, and it could be attached to the value 2015 for Alice and Bob. But things can get a little bit more complex. You can have different types of relationships, so not just friends, but Jim and Chad are colleagues. They're also users in the system. And you can have more. So you can have boss of, you can have married to, you can have loves. A funny part of this figure, this came from a textbook, but I noticed that in the bottom left-hand corner, the textbook authors sort of cheekily made a love triangle, which I thought was funny. I love it when textbook authors try to insert a little bit of humor on the sly. But so note that all of the nodes in this current graph are users. It's possible in graph databases to have nodes that are of different types. So for example, you could have a letter node, and an example property could be the contents property, I love you. But this is just a graphical representation of what graph databases can contain. Okay, so why am I talking about graph databases? It turns out that, so this is the efficiency part that I mentioned. Graph databases end up being very fast to query for certain types of questions that you want to ask of the data. So for example, let's say that you wanted to find, for every user, their friends of friends. So I'm going to call this friend squared. So like, for example, Alice is friends with Bob, who were Bob's friends. If the data were stored in a traditional relational database, so a series of rectangles essentially, the query would take 0.016 seconds, and in a graph database, it would take 0.01. So like not a huge difference there. But let's say that I wanted to find friends of friends of friends, so friends cubed. If I had stored this data in a relational, typical rectangular database system, that would have taken 30 seconds. And in a graph database, it would have taken 0.16. And finally, friends to the fourth, it would have taken an absurd amount of time for the relational database to find all of these instances, and much, much, much less time for the graph database. So graph databases end up being fast to query. And just to tie back into our overarching motivating context, you know, if we're organizing all of human knowledge, say that was possible. If we're organizing human knowledge in databases like this, it makes sense that we would want to find a system that is as efficient to query as possible. So another reason why graph databases end up being useful for this use case is that they facilitate connected queries a lot more than relational databases. So, you know, a lot of interesting questions that we might ask of our data in a setting like this are connected ones. So for example, who are the friends of those who wrote letters? That would be much harder to answer in a relational database. You'd have to imagine having one spreadsheet for letters and who wrote letters, and then you'd have to have other spreadsheet for friends, and you'd have to do this sort of back and forth lookup over and over again to really get the answer to that question, but it ends up being a lot better in a graph database. So another example, do colleagues tend to be friends? What other relationships do bosses tend to have? So the overarching characteristic of these types of queries is that they're all about relationships. And that ends up being much harder to implement in traditional relational databases and much more effectively represented in graph databases. Okay, and so admittedly, I'm not an expert on graph databases. I'm learning about this ongoing, but I just wanted to give an overview of, you know, so I've talked about querying graph databases such that you could find patterns in the data stored in them. One way to do that is the Cipher query language. I don't know if there are others, but this is at least one that I know about. So for example, a way to find, let's say that you were trying to find it within your database, people who are married to other people. So there's this really expressive syntax where essentially the part on the left of the query is, you can kind of, if you complete the circle around the parentheses, it almost looks like a node, and that's intentional. This Cipher query language is meant to kind of be as visually representative as possible for what are you searching for on the left, and how is it connected to things on the right. So in particular, I'm trying to search for people who are married to, and that's kind of nicely visually captured by this arrow. And the married to inside indicates I want these arrows to be married to arrows. And what you're specifying on the left and right are, you know, what type of thing, what type of entity, what type of node in your system do you want to find being married to things on the right. So I'm not going to talk a lot more about Cipher, but I just wanted to make known that there are really cool and expressive query languages for graph databases that allow you to answer the very connected questions that I just talked about. Okay. All right, so kind of that was an overview of graph databases, but kind of tying it back into the context that I motivated at the beginning. So structuring knowledge, can we get to this great level of understanding to be able to say it's just a, so in Daniela's case, it's just a linear model. What is the structure of knowledge? Can we use graph databases to structure knowledge? For me, I'm interested in statistics, but in general, how can we use graph databases to structure knowledge in a general field? Okay, so I'm gonna give it a try. At least this is my level of understanding. This is a tiny, tiny graph database for Daniela's tweet. A linear model is just a linear combination of things. And so, for example, a spline function is also a linear combination of things. And it generally happens to, spline functions end up being incorporated in linear models via least squares. And lasso is also a linear combination of things. It just happens to be fit via a different method, penalized least squares versus ordinary least squares. So like, yay, is this the right structure for the knowledge that Daniela is capturing in her tweet? You know, this was my first pass at it. This is my level of understanding. I can see why she described all of the various things in her tweet, splines, lasso, and ridge regression. I can see why she called them just linear models, because they're just linear combinations. But is there a more effective way of structuring this knowledge? Maybe a better way is this. Maybe I had to break it down a little bit more into sort of more fundamental atoms. So a sum of linear terms is a linear combination, and a sum of cubic polynomial transformations is a spline model. These two sort of statements have the same structure because of the sum of is a. Is this how I should represent the knowledge that, you know, a spline model is just a linear combination, is just a linear model? I don't know. But one small caveat, it's really, so as written, I don't think that this is the best representation because the is-a only links linear terms and linear combination. It only links cubic polynomial transformations and spline model. Really what I meant by this sentence as a whole was sort of the aggregate. The sum of linear terms as one entity is a linear combination, and the sum of cubic polynomial transformations as one entity is a spline model. So this ends up being a particular sort of challenge, at least for me as a novice, in thinking about how to model this data with graph databases, because really I have to think about aggregating multiple concepts to relate the aggregate concept to a broader concept. And so broadly, I can characterize this challenge as one of how to best represent, in a sense, very, very hierarchical knowledge, right? These atoms sort of fuse together, these atom ideas fuse together to form bigger ideas, which fuse to form bigger ideas and bigger ideas. And a lot of the time, that's how knowledge is structured. So I don't have an answer to this question, but it's something that's on my mind. And also just sort of language. Like, let's say that I wanted to express this sort of relationship between variable transformations as being a part of a linear combination. So is it better to say variable transformations are a component of a linear combination, or is it better to say linear combinations can contain variable transformations? The sort of richness of language issue is also really hard, and I don't know if I know the answer, but it's something that I'm thinking about. So kind of where this led me to thinking was, so I deal a lot with R, and I do all of my sort of traditional rectangular data management with R. I'm so used to thinking about rectangular data. So in particular, in R, there's this tidyverse ecosystem which allows for working with and wrangling data in different formats. And there's a rich vocabulary for dealing with sort of the traditional wide and long data. We can pivot longer, we can pivot wider. And it struck me that like that is all really solidly in my head for rectangular data, but I am thinking a lot about developing a mindset and thereafter tools, like software tools, for thinking about and reshaping quote unquote graph data. It was just an analogy that I thought of that I think is not well developed for me. Okay, so I want to show, let me check how I'm doing on time. Okay, I want to show one more example of how I try to, how I'm thinking about trying to build knowledge graphs for these insights that I'm getting from research articles. So I'm going to try and tackle the last one. Principal stratification, which is a method within causal inference, is not appropriate for mediation analysis. So behind me writing that statement, I realized there was a lot more to unpack. So I tried to break it down kind of like this. Principal stratification is a method. Mediation analysis is a method. So I characterize those on the ends. And both of these methods estimate quantities. So in principal stratification, the target estimand is actually something called a principal effect. In mediation analysis, the target estimands are things called direct and indirect effects. And when I said principal stratification is not appropriate for mediation analysis, I had in my head this graph structure. It turns out that the estimands that are estimated in principal stratification are only interpretable as one of the quantities that are estimated via mediation analysis. And sort of like the lack of an arrow here was my way of capturing, was what I meant when I used the hashtag not appropriate for. Okay, so I try to show some graph databases, very small ones for some different situations. And you might be wondering now, is this overkill? This seems like a lot of work to kind of just represent meaning in text. I think not, though. So another quote from Range. This is a really good book, and I recommend that. I recommend it to everyone. So another quote from this book is on the subject of something that was called the Good Judgment Project. So a little bit of context. Decades ago, there was a government-sponsored forecasting project related to just predicting things in a lot of different areas. And a lot of the predictions centered around making forecasts about foreign affairs. So this quote has to do with one of those forecasting challenges. So for example, in 2015, forecasters were asked if Greece would exit the Eurozone that year. No country had ever left. So this question seemed totally unique. However, there were plenty of examples of international negotiation failures, exit from international agreements, and forced currency conversions that allowed the best forecasters to ground themselves in what usually happens without focusing narrowly on all of the unique details of the present situation. So what I pull from this quote is essentially a conclusion about pattern finding. Essentially, the forecasters had really great mental models of a lot of different situations. And I read that as they had really strong graph databases in their heads of lots of different instances in history. And they were able to mine their internal graph databases for historical patterns, for historical examples that would allow them to predict a seemingly unique sort of foreign affairs situation. So that quote reminded me of something that I've thought a lot about, which is the idea of creativity. Creativity, I feel like, is often described as this sort of mysterious and magical quality that if you have it, you're awesome, and if you don't have it, you wish you had it. Really, I've internalized creativity as making connections between seemingly unrelated ideas. And, I don't think that we should view creativity as this sort of mysterious arcane quality that only some people have. I think that all of us are capable of being creative, essentially. And how I hope that will happen is honestly via graph databases. I'm wondering, can we build systems to computationally find patterns in human knowledge? And you can read this as, might we be able to use graph databases to represent human knowledge so that we can easily find patterns like those great forecasters did in the Good Judgment Project? And another really, so I'm getting close to the end. So another really cool example that I've seen recently in the sort of the data science education context of essentially graph databases are these concept maps that RStudio is putting out for learners. So this happens to be a concept map, which let's call it a graph database. This is a graph database for the dplyr package. And so you can see that the nodes are sometimes different functions inside the package, but there are all these really rich connections between functions and aspects about data. I'm wondering about this, like, can we build graph databases to essentially, improve how beginners learn data science tools, but also study how people, not necessarily just beginners, but advanced users use these different data science tools to work with their data, because we're data scientists. We know that if you hand a certain task to different data scientists, it'll be done in completely different ways. Do these graph databases shed light on how that's happening? I'm really curious. Ooh, I was supposed to delete that. Okay, so I want to sum up. So the problem that I introduced at the beginning is that human knowledge is overwhelmingly vast and it's very tech-centric. There's just so much that we have to read in order to effectively gain sort of the cutting-edge insights that our peers very valuably are contributing. And I'm wondering, can we create graphical, computable digital relics from text knowledge? And I'm wondering if we can find good forms for those digital relics. In other words, can we find good forms for building graph databases that can facilitate computational pattern finding? I think that will be a really powerful way forward for onboarding like newcomers to the field. How can they most effectively and quickly learn all of the meaningful knowledge there is to learn within a field? How can we find insights and make patterns and connections between different fields? That is, all of this is centered around these ever-present thoughts in my head. But that is all I have, and I'm happy to take any questions.
Thank you so much, Leslie. That was a really cool presentation. And if you didn't say you were a novice, I would not have thought you were a novice. We do have a question from Frank Catwell. So the question is machine learning a version of gathering knowledge computationally?
Sorry. Can you repeat that one more time? My cat is meowing and is distracting me.
Okay. So the question is machine learning a version of gathering knowledge computationally?
I would say yes, but machine learning is the kind of the approach that I've talked about here is a little bit disparate from machine learning. In machine learning, kind of data has to arrive to you already, and algorithms then work to find patterns in that already collected data. I guess what I'm talked about here is even before that happens. What I'm talking about here is data gathering, honestly, and storing data in a way that we might be able to perform machine learning on data stored in graph databases, but the data are not, knowledge is not in that form right now. Knowledge for the most part, is in text. It's in papers, it's in books. Often, sometimes it's in oral histories, but it's not in a form that is computable yet. It's not in our traditional data form.
Mm-hmm. All right, any other questions for Leslie? Well, we still have 5 minutes, so, yes, Fiona Adams. So the question is, what do you imagine are the next steps?
Yeah, that's a great question. I am honestly just trying things out. So for example, I'm still working on this. I'm still trying to read and trying to transcribe what I think are the nuggets of insights into forms like this. And honestly, it's kind of like this back and forth of exploratory data analysis. If I can get a graph database of a substantial body of papers and start making queries to understand patterns, like, is a concept of a method linked in a particular way to concepts of sort of issues that arise in different research settings. I can ask those types of queries and see if I'm finding patterns. This is work that is very much ongoing, and it's very, very experimental.
Mm-hmm. Cool. And another question from Inaida. I'm sorry if I said your name wrong. So the question is, how did you get involved in this field?
By happenstance, I was actually advising a student summer research project where I was working on something completely different. I was trying to I was trying to build causal graphical models from text, mm-hmm. and I stumbled upon a database of essentially biochemical reactions that was stored as a graph database, and I was like, what in the world is a graph database? And so I ended up learning a lot more about it, and my thoughts led me here. But it all started with randomly learning about graph databases.
That's really cool. Yeah. So the next question is, I'm so happy that everybody is so engaged. You do have a few more questions coming up. From Amber, outside of R, are there other ways or software to create these graph databases? So Frank had mentioned Neo4j. Is there anything else out there?
I only know about Neo4j. So Neo4j is, I think they are the ones who create and maintain the Cypher query language. I want to give a plug so Denise is giving a talk, I think, next,
right after
also about graph databases. So I think she would be a great resource and answer to a lot of these questions too. I only know about Cypher. There is actually an R package that interfaces Cypher with R. It's called Neo4R, but you need to have Neo4j installed.
Mm-hmm. And then, so like Magna, I was also intrigued by the note-taking stuff that you had. So, oh wait, sorry. I thought it was really cool, and the question is like, what was the tool that you used to do that note-taking?
Oh, this is another can of worms. So I went on this sort of productivity binge this summer. This is a note-taking tool called Roam Research. It is not free. It is, you'll notice, well, here's better. It's called Roam Research. The new feature with these are called networked note-taking apps. Mm-hmm. And the feature of that is that these links that are colored in are what are called bidirectional links. So whenever there's a page called ISA in my database of nodes, and when I click on ISA, I can see all of the instances where ideas were related by the linking verb is a. So Rome research is one. I'll also say that Obsidian MD is another. It's free and purely based on Markdown.
Okay. One last question, since we're running out of time. So a question from Talia. How would the data from a graph database be displayed in visualizations, or at least presented to a consumer?
That's a good question. I would say that this is something that would have to be engineered. But for example, if you were able to find a small enough representation, a small enough subset of your data, you could display it in exactly this form. Neo4j actually has a viewer that shows the results of the query in graph form. So this could be a way. But I think that a good analogy is that of maps, like actual like global maps. Like when you zoom in on a map, you're not literally enlarging the picture. You're actually seeing a completely different picture of, you might see a state at one level, but if you zoom in, you actually see the county level structure. If in cases where your graph data are hierarchical to that extent, I think that sort of zoomed in and zoomed out views end up being more effective. The technology end of actually how to do that, I'm not sure, but that's kind of my recommendation from a conceptual standpoint.
Well, thank you so much, Leslie. This was awesome, and I hope the attendees learned just as much as I did from your presentation. So we have 3 minutes until our next session, and we'll see you all there. Thank you so much.
Thanks, Kim.